My background is machine learning and algorithms, and I'm going to tell you a bit about deep learning and the understanding of deep learning. So we have witnessed that deep learning has made a lot of breakthroughs in many sub-areas of artificial intelligence in the last few years. So these include computer vision, robotics, natural language processing, and the common technique behind all of these breakthroughs is the use of neural networks, and in particular, deep neural networks. So how does deep learning work, and how do we make it better? So if you want to use deep learning or machine learning in general to some question, then probably you have to go through some of these steps. So first of all, we have to formulate our problem as a machine learning problem, and then probably want to collect data, training data and test data. And then we want to design our model, and sometimes this is deep neural networks. And we may want to use some optimization algorithms to train the model. And then we probably want to test the performance of our model on the test data. So deep learning is often referred to as this model design phase where we just go deeper with neural networks. But I have to argue that deep learning is not only about this phase. So I like to use one of this metaphor, of this theory of constraints, or the big law of the minimum from management science as a metaphor. So it says that the capacity of a barrel is limited by the minimum length of its staves. So in some sense, in the last few years, what we have been doing with deep learning is that we increase the model design part of the stave. And I think in the future, we have to work on all of the other staves as well, the training, the testing, data collection, so on and so forth. We have to understand all of these modules to make deep learning better and better. And moreover, another thing I haven't told you is that this is not really a pipeline in reality. When we really do the research and we want to develop some new algorithms, there are really a lot of back arrows here. We have to really go back and forth between all of these modules. We have to think about training, and maybe the training doesn't work, and we have to go back to the model design phase or the data collection phase, and so on and so forth. So we really have to understand the interactions between all of these phases. So, and if you can do that, we can understand deep learning better, then the hope is that this can lead us to design more accurate models to speed up the algorithms, to improve the data efficiency, to enhance the reliability, and so on and so forth. And finally, I hope that understanding of deep learning can sustain and boost the progress of deep learning. So this is kind of my main research mission, and let me tell you some of the examples of my work along these lines. So the first example I'm going to talk about is understanding word embedding, word vectors. This is the same thing as James talked about, so I just call it word vectors. So this is about understanding the modeling part of deep learning, and I'm also going to talk about the bright side of it instead of the dark side, and understanding of the black side. So as James in James' talk, so the main idea here is that we want to store the semantic information of words in vectors so that we can use them. So just recall, we want to kind of encode the word into vectors, and the vector is a list of numbers. So I have a 4-dimensional vector here, and often we are talking about really high-dimensional vector in reality. And we also want to encode the relation into directions. So this is just a different way to define this analogy task. So if you look at where these words are in the high-dimensional space, each of these vectors corresponds to a point in the high-dimensional space. And here I'm just drawing the 2-dimensional space. And these red dots are where these words are. And interestingly, this direction corresponds to the country-capital relationship. And this also applies to other relationships like a gender relationship and, for example, country-currency relationship, so on and so forth. And the mystery that we want to explain here is that why we can kind of embed or encode all of these vectors into all of these words into vectors so that we can have these nice properties. So in some sense, the kind of questions we want to understand is how do we link the semantics of the words with the mathematical structures of these vectors. And the explanation we found is that they can be linked through the correlations between words. And actually, the first connection here between semantics and correlations, this is an old theory in linguistics, proposed by Harris and Furse around 60 years ago, which is called distributional hypothesis. It says that the meaning of a word is determined by words it co-occurs with. And what we have done here is complete the other connection here between the correlation of words and the mathematical structure of the word vectors. So we design simplified probabilistic models for the language, and we derive these connections formally from this probabilistic model. So this is a theory that explains why we can link the semantics to the mathematical structures of the vectors. And based on the theory, inspired by the theory, we kind of extend it to other more settings. For example, one of the settings we can do is that we can also assign vectors to meanings instead of just vectors, instead of just words. So many of these words have multiple meanings, and we call it polysemous words in linguistics. And the ideal case is that we want to represent a polysemous word, a word with multiple meanings, as the sum of its meanings. We represent each of these meanings as also vectors, and take Thai as an example. So Thai has probably a lot of meanings, let's say 5 meanings. And what we like to have is that the vector for Thai is a sum of the vectors for all of its meanings. And indeed, we can do this by designing some algorithms inspired by the theory in the previous slide. And what we found is that we found 5 meanings or 4 meanings of Thais, and we visualize these meanings by the word that it correlates with. And you can see here, the first meaning, the first column, is really about the clothes meaning of Thai, because all of the words there are correlated with clothes. The second and third columns are about equalizing in a game, the meaning of Thai as equalizing in a game. And the second column seems to be more about equalizing in a long run, and the third meaning is more about equalizing in a particular game or match. And the fourth meaning is about the action meaning of Thai. The last one is not that coherent or relevant, but it seems to be relevant to different types of Thais in musical situation. So let me just mention that these are only trained using Wikipedia documents. We don't know these meanings of Thai. The only thing we are given are the raw documents on Wikipedia, and we found these meanings, and we found the vectors for all of these meanings. And we can also extend this to use this to cluster words with similar meanings. So we have a very large vocabulary size, like 6K words, but here, let me just show a subset of them and subset of the clusters about those scientific words. So we found these small purple clusters. For example, a cluster about graph theory, a cluster about logic, some cluster about number theory, so on and so forth. And then we can also cluster these small clusters into big clusters, which are more general topics, like math, physics, chemistry, and biology. And you can see that this small cluster sometimes belongs to 2 big clusters, like biochemistry belongs to both chemistry and biology. Let me just mention that some of these clusters might be a little more difficult to find than you thought. In the logic cluster, we have words like logic, deductive, propositional, and semantics. These are kind of words that I know because we are dealing with these kind of words every day. But if you look at the polymer cluster, actually, I don't really know these words a priori without Googling online. And we only, the only thing we need is the raw Wikipedia documents online. So the cool thing about this idea is that we can also extend this to even more general setting, which I call like vectorizing everything. So we can vectorize words and meanings. We can also assign vectors for sentences. We can also assign vectors to documents. And if you are doing some personalized service, maybe you can assign vectors to individuals. You can assign vectors to products. And the key idea here is that on the left-hand side, we have these concepts that are understood by humans, and we kind of translate or kind of encode them into vectors which can be understood by machines. And if you know how do we encode, how do we do these encoding steps, then we can also have the reverse direction so that we can understand what the machines are doing with all of these numbers. So this is about understanding the modeling part of deep learning. And now let's move on to another example about understanding and improving the training process of deep learning. So speaking of training, often the first question that people ask is, how do I train faster? How do I save more time in training? But I like to say that there is an even more fundamental question: what functions or models are easy to train? My research concerns about both of these questions a lot, but today I'm only going to talk about the first question because I think it's fundamental and also it's highly relevant to the final quality of the solutions we found. So the current understanding about the first question is that a function is easy to minimize if all local minima are also global. What do I mean by that is that this function is actually not easy to minimize because on the left-hand side there is a local minimum there, and this local minimum is not a global minimum. So if we converge to the local minimum, no matter how fast we converge to there, it's not a good solution because it's not as good as the global minimum. However, this function on the right-hand side, this is a function with the property that all local minima are also global. And now we are happy because whatever, no matter which local minimum we converge to, we are happy because they are both global minimum. So now we understood, what functions are easy to minimize. And the next question is, how do we kind of translate this to, next question is, how do we make a function easier to minimize? So that's this idea called a landscape design or reshaping the laws, which we want to use it to make the training easier. So let me give you an example about a toy case. This is a two-layer network. We train a two-layer network with the standard algorithm and standard laws, and this is the plot of the training error versus iteration. So now on the x-axis, I have the number of iterations. On the y-axis, I have the training error. And you can see that in this standard case, the training error drops very fast at the beginning, and then the training error plateaus around 0.1. And it just stops improving. However, if you design a better loss function, in this case, and use the same algorithm, and you shape the loss function, so what happens is that the training becomes a little slower, but the test error does converge to, the training error does converge to 0 in this case. So we get a better quality solution compared to the previous case. So, and what exactly happens, behind this is that on the left-hand side, the training operating function we are, minimizing is something like this, where our algorithm somehow converges to that bad local minimum, and they can never, get out of that local minimum. So that's kind of why the training error is not great. And on the right-hand side, we reshape the loss function, and the loss function becomes this nice function where all local minima are global. And that's kind of why it doesn't matter which local minima we converge to, we are happy. And the key to achieve this kind of reshaping loss or landscape design is that we have to understand the mathematical properties of these high-dimensional non-convex functions. We didn't understand them very well because we didn't use non-convex functions as much as we do now, and now we are developing new algorithms, new mathematical techniques to understand these non-convex functions. So, so the next example I'd like to talk about is reinforcement learning, which I think, in my opinion, is pretty much about the interaction between the data collection modulo and the training and optimization modulo. For example, if you want to beat the top player, the Go player, then the algorithm you want to use is something like this. At a very high level, it does the following thing. It tries some strategy, you maintain some strategy, and you try the strategy and collect the feedbacks. And you know whether the strategy can work or not, whether you win or fails, and then you improve the strategy based on the feedbacks. And then you go back to the data collection phase, you collect more samples, you collect more feedbacks by trying the strategy, and then you prove the strategy, and so on and so forth. So the beauty of this idea is that it works super well for Go, and now we can beat the human player. However, the limitation here is that it requires a lot of trials and samples. And for Go, we have to collect millions of trials to beat the top players. So this is kind of prohibitive in the robotic setting, where we don't want our robotic arms to try 1,000,000 times. So, what I really want to talk about is the model-based reinforcement learning. This is a new idea that potentially can solve this data efficiency problem. So what I mean by model-based reinforcement learning is that we are modeling the dynamics of the physical mechanisms of the world, and so that we can anticipate the future. So, and then we can revise this paradigm a little bit now. So on in the data collection phase, we collect strategy and collect feedbacks and observations of the physical states. And then, based on the feedbacks and observations, we improve the model of the dynamics, or we improve the prediction of what happens in the future. And then based on this anticipation of the future, we improve the strategy. So because now we are using more information about the physical states, and we get the sample efficiency. And people believe that if we do this well, we can improve at least 1 magnitude on the sample efficiency. And another possibility is that we can, this idea can generalize to other tasks with the same environment, because we have a model for the environment, for the dynamics of the environment. So this is a very active research area in the last 1 or 2 years. And let me just show you some recent ongoing work. This is maybe a little raw, and this is an ongoing work to try to, let the, this is a very tall example. We are just trying to let this kind of a simplified snake to slither to the right as fast as possible. So recall that we have to maintain a model about the world so that we can anticipate what happens in the future. So in the first round, this is what the snakes anticipates in the future. It's kind of like daydreaming, as you will see. So it thinks that it can kind of thread through the surface without that violates the physical law. And this is what really, in reality, the snakes can do in the first round. So it doesn't really move much. And then the snakes takes all of these observations into consideration and improve its strategy and improve its anticipation of the future. And in the next round, you can see the snakes anticipate much better. So you can see that it's kind of understand that it can move forward a little bit, but at the end, that anticipation is a bit off. It struggles a little bit. And this is what it really does in the reality. It works a little bit at the beginning, and then it stops working. And in the third round, after further improving the strategy and the model about the world, then the snakes is doing much better, even in anticipation. And in reality, it also does much better, as you can see. It starts to know how to move forward. And if you train this longer and longer, you'll see that the snakes anticipate the future better and better, and it starts to move faster and faster. So just as a summary, so my main research mission is to understand and develop deep learning algorithms. And I like to use this metaphor of Lebesgue barrel again. So I think we have to improve on different aspects of deep learning. We want to make the model more accurate. We want to make the model more interpretable. We want to make the training faster. We want to use fewer examples, and we want to make the model more robust, and so on and so forth. And I think using more mathematical tools, we can make deep learning better in all of these aspects. Thanks.
Very good. Questions? I'd like to see from up here. Well, while people cover the question, let me just have a request for you. I was intrigued by your comment about representing individuals by vectors. So when you find my vector, can you please let me know? I'd like to have it engraved in my tombstone. Here lies 27, 18, 53, 7.
Okay.
That will be the Hector vector.
That's right, a Hector vector, perfect.
Yeah, you have to first give me some training data.
Well, here I am.
Yeah.
Anyway, so we have a question. Let's get the microphone for you.
Interesting talk about interpretability. How are we going? How are we doing there? Do you have any like comments on that?
Yes, I think there are multiple levels of interpretability. So one level is you want to make the model interpretable for the users. For example, if I use Google Map and I want to request some navigation service, and I want to know why Google Map gives me this route instead of the other routes. So that's the user level interpretability, and I think we are doing well on that side. And there are a lot of recent work on designing models that not only just give you a prediction, but also gives you explanation why the model wants to do it. And there's another level of interpretability, which I think is equally important. This is interpretability for researchers. So we want to understand why all of these models are working and how do we improve on them. And this is more about, this is basically what I was talking about, in part of this talk. And I think we are also making a lot of progress on those directions. But we need more mathematical tools to understand better.
So we have one question here and then one back there, and then we'll wrap it up.
Yeah, about loss functions, depending on the context, you already know whether to use softmax or conditional log likelihood and so on. But is there a methodology for choosing the optimal loss function, as you were pointing out?
Yes, that's kind of what we are looking for. And even when you talk about softmax or logistic loss, right, these are actually also surrogates for the loss we want to really solve. We really care about the accuracy, the percentage. And the logistic loss is just a surrogate. And yes, we are working on all of this. And one of the methodologies to think about which loss function makes optimization easier. And another way to think about it is that which loss function makes the so-called generalization better, meaning which loss function can give you better test result. So I think there are different types of methodologies to study both of these perspectives. Yes, but we need more progress, of course. I don't think there's a systematic ways to think about it for the moment. But in some sense, we also have to think about different situations, differently in some sense.
So related, when you were talking about reshaping the loss function, you're really talking about numerical conditioning and numerical optimization, right? Not changing the whole, loss, the modeling of the loss function, if you will, right? It's more having to do with numerical conditioning and optimization.
Yes and no, in the sense that yes, the goal is to make the numerical optimization better, but to achieve that, we can change the model. So this is additional flexibility that we can allow in machine learning. We don't really care exactly about which model we want to use. You can use a ResNet, you can use a VGG, all of these different models, and as long as the prediction is good. So actually, what we are doing is that we change the model and the loss function together so that it does the job, so that it makes the optimization easier.